Hello, hello. Fix my mic.
And that one. Okay. So we looked at addition and subtraction of integers earlier, and my tools are missing too. Wrong button. Screen. There we go. There they are. All right, so let's take a look at multiplication, seriously, of integers. So we'll look at a couple of examples, and we'll take a look at activity 6, and we'll do division, and we have chapter 5 in the bag. All right, so we have a couple of definitions of multiplication that could help. One, most popular, is groups in. And second popular one is repeated addition. Okay, and so we'll attempt to use those to figure out what to do with integers. So let's take 2 times negative 3. Multiplication means almost that I have 2, literally multiplication is groups of negative 3. Yeah, so this is translated as 2 groups of negative 3. So then we need a model for what does negative 3 mean. And we had that one model is the chip model or the charged particle model. So we could say that right there is a 1, maybe that right there is a negative 1, and then if I put 2 of those together, then I get a 0. So integers are a little more complicated than whole numbers, so we usually need a key to go with it. So then here would be one group of negative 3, and I'm going to combine that with a group of negative 3. And put it together, and we get a group of negative 6. So that works out pretty good. Trouble comes when we try to do something like negative 2 times negative 3. Because how do I interpret that negative right there? So, I mean, I can write negative 2 groups of negative 3, but I don't know what it means to have negative 2 groups. I know what it means to have 2 groups. So this is trouble. So how do we interpret that? One way we could interpret it is by saying here, because that was really a positive 2, what I was doing was adding 2 groups of negative 3. So over here then, I might try that negative out front means to take away. Two groups of negative 3. So going back to the other problem, here I started with nothing and then I added 2 groups of negative 3. Same thing's going to happen here. I'm going to start with nothing. So at the moment, I don't have anything to take away, but aren't there other ways to represent 0 in this system? 0 could be nothing, or how else could I show 0? Positive and a negative. Yeah, so I just say, okay, well, I still have nothing. And so that's one key here. I have to start with nothing. Start with 0. I don't have two groups of -3 though, so I start building. So I need two groups of nothing. Am I at a position yet where I can take away two groups of -3? Not yet. So I keep building. So now I can, after I build, so now take those -3s. So I'm going to take that group of -3 and that group of -3, and what's left, so that leaves 6. Okay, so just like we started off with what addition and subtraction meant with these toys, we can continue on that theme, and now we can do multiplication with it also. Okay. All right, so let's look at it a slightly different way. So take out activity 6 from the book. I'll bring up my copy. We'll get this sucker done. Let's see, documents, math to 11, activities, chapter 5. Yeah, we're going to skip it for now, though. Let's get this done. So here what I want to do is use patterns with multiplication to come up with a way to show what the different products are. So here we have a pattern where it's 4 times 3, 4 times 2, and so on. So let's fill out that pattern. So sometimes this is called a pattern model. And you can use it for addition, subtraction, multiplication, division. So we're going to start off by saying, okay, we know from previous work 4 times 3 is 12. We know 4 times 2 is 8. We know 4 times 1 is 4. And we know 4 times 0 is 0. So from our work with whole numbers. And so what we want to do is just continue the pattern. So in the second column here, I've developed a pattern 3, 2, 1, 0, and I want to continue that pattern. So after 0, what's the next popular number in order? Would be -1. So here I'll have 4 times -1. Now in the next column, I have a pattern going down also. And so in this column, to get from 12 to 8, I drop by 4. To get from 8 to 4, I drop by 4. Oops. And so on. And so in this column over here, I just keep dropping by 4. So if I'm at 0 and I just lost 4, how much do I have now? I have -4. And then we can continue that pattern. 4 times in the next column, -2. According to the second pattern in blue, if I drop by 4 again, should give me -8, and so on. So we do a few of these patterns, and we kind of see something happening here. If I take a positive number times a negative number, the answer seems to be negative. So we're just kind of make a conjecture here. That a positive times a negative seems to be a negative number. So we've got part of this worked out. Let's 4, 3, 2, 1 times 5. Yeah, let's take a look at pattern number 2 here. We're multiplying by 5, but in the second column. Oops, wrong way. So I have 4 times 5, 3 times 5, 2 times 5, 1 times 5, 0 times 5. So whole number pattern that we're pretty familiar with, 20, 15, 10, 5, 0. And again, we've got two patterns developing here. We've got the integers coming down this way. So 4, 3, 2, 1, 0. Next number ought to be -1 and -2 and so on. Pattern on the other side, how would you categorize that pattern? They're just dropping by 5 each time. So we just make a note, we lose 5, lose 5, lose 5, lose 5. Close that. I think we might get a rant over there. All right. And we keep dropping by 5. And so the next obvious number then would be 0, lose 5 is -5, and -10. So if we change the columns for the pattern, it doesn't seem to matter. Doesn't our conjecture still hold? We had before a positive times a negative. Here we have a negative times a positive, and the answer is still negative. And that kind of fits which property? Would that be the associative property for these two rules or commutative? You remember? Yeah, because they physically switch place. Yeah, so the commutative property is playing in here. It doesn't matter whether we take a positive times a negative or a negative times a positive. The answer still seems to be negative. All right, so that's kind of cool. And worksheet's guiding us further. Here they say, let's just take a negative number, constant, in one column, and then go through integers in the other column. So part 4. So we've got -3 times 2, -3 times 1, -3 times 0. And our work earlier seems to imply that a negative times a positive should give us a negative answer. And I know that 3 times 2 is 6, so I think the answer here should be -6. We have another rule, a number times 1 is itself, -3. That also makes sense with the negative times a positive rule. And then anything times 0 is 0. And so then we're going to continue this pattern. We have 2 of them. We've got the integer pattern we were playing with before. So 2, 1, 0, -1, -2. What's the pattern happening in the third column? -6 to -3. Yeah, this time we're adding 3. And a number line's a nice way to do this. We're just doing it horizontal. And so from 0, if I add 3, 0 plus 3 should be a 3. And so here I have -3 times -1. And usually when there's a bunch of symbols stuck together right here, we put them in parentheses to be safe, especially the second number. So that would be -3 times parentheses -1. -3 times parentheses -2. Continuing that pattern of adding 3, then it seems like this should be a +6. Well, we know that 3 times 2 is 6. And our earlier conjecture was that a negative times a positive is a positive. So here we seem to be getting another conjecture that if we take a negative number times a negative number, we get a positive number. Right? So we can show it with patterns. That also works with what we played with before. when we, starting with nothing, we take away two groups of -3. That also gave us a positive answer. Okay, so we have a bunch of evidence leading to this. And so what these different rules are, the negative times a positive is a negative, and the negative times a negative is a positive. It doesn't matter how big or small the numbers are, this is just a set of rules we apply. And a set of rules is called an algorithm. So what we've just done is we've developed an algorithm for multiplying integers. And there's two ways that you can write this. So here we started with a positive times a negative, and then the next pattern led us to a rule for a negative times a positive. What do both of those scenarios have in common besides that the answer is negative? What does the negative times a positive, how could I characterize that slightly differently, both those situations in one shot? Yeah, opposite sign. Yeah, that does it right there. So we have one rule that takes up those two things. Just say, hey, if they're opposite in sign, the answer has to be negative, which is kind of cool. Now, let's write that down in our algorithm. So if the numbers are opposite in sign, then what we have is a positive product. So the product is positive. A negative, oops, thank you. Jumping ahead to the next part. And remember, the word product is just the result of multiplying two factors. So that's part of our rule. And one of two things is going to happen. Either the numbers, there's two numbers, so either they're the same sign or they're different signs. So here we have their different signs, so our other rule will be for if they're the same sign. And that's when we'll get the positive product. And I think I forgot a word here and there. And so otherwise, multiply as usual. Because we still have to come up with the product. All this tells us is the sign of the product, right? All right, and I think we've mostly got this done. We have part 3, multiplying a positive times a negative, multiplying two negatives. We generalize that a little bit more to being the same sign. What else did we have here in this activity? Excuse me. The idea of inverse operations. We'll take a look at that. And then we're not doing activity 7. Okay, so let's finish the second box down here. So here they're saying recall multiplication and division are inverse operations. So as far as division is concerned, there's one quick way to deal with an algorithm for dividing integers. one of our algorithms from before was the missing factor model, or sorry, algorithms, and I meant models. So division, missing factor model. An example of that, 12 divided by 3 equals what? Instead, we rewrite it as a multiplication. What times 3 equals 12. And essentially all we have to do is read it backwards to get that. So can we pull off the same thing with integers? So what if I had 12 divided by negative 3 equals what? So I rewrite that using the missing factor model, and that gives me what times negative 3 is equal to 12. So now I'm back to multiplication. So we have rules for multiplication. The rules for multiplication, when do we get a positive product when multiplying integers? To the same sign, right? So if one of them is negative, the other one has to be negative. So right away we know that the box has to be a negative number. And then we just think, well, what times 3 is 12? And we mess around with our products, or we just remember it. And we say, well, it's got to be negative 4. So now we have an answer for 12 divided by negative 3. So let's just play around with that for a little bit, looking at patterns. We've just established that 12 divided by negative 3 is equal to negative 4. Let's take a look next at negative 12 divided by positive 3. Oops. And so we apply our missing factor model, which means write it backwards as multiplication. And then reflecting on our multiplication algorithm, what's got to be true if I have a negative product? Oh, shit. Thank you. That's 12. Oops. That's not an eraser. If I have a negative product, what has to be true about the factors? Opposite in sign. Okay, so we know that we have opposite signs. So the missing number has to be a negative, and then dipping into our rules that we know, 4 times 3 is 12, so it's got to be a negative 4. Okay, so up here, the missing number has to be negative 4. And so we can do this a bunch of different times. Do those examples lead us to a possible algorithm for division? Okay, what do they tell us?
Dividing opposite signs, the answer is going to be negative.
Yeah, so it's pretty much the same as the multiplication algorithm. And then let's just try it out. So again, here we have opposite signs. Just a summary lead to a negative. Do you remember what the answer to a division problem is called? A quotient, right on, to a negative quotient. So that seems to match multiplication. So then the hope is if we divide numbers of the same sign, we'll get a positive quotient. So let's just double check that with a couple of examples. We know if they're both positive, that works out. So what we need to check is what happens if they're both negative. So what if I had negative 12 divided by negative 3? And then we'll use our missing factor model. So that gives me what times negative 3 is equal to negative 12. So reflecting back on the multiplication, we know that to get a negative answer, that these have to be opposite signs. So that means my missing number has to be a negative. Oh, shit, right, positive. Thank you. And we know that 4 times 3 is 12, so it looks like the candidate for a missing number is 4. And so that fits the idea that the rules for division of negative numbers are the same for the rules for multiplying, at least for determining the sign. So dividing numbers of the same sign lead to a positive quotient. And I think that's about it for that activity. So we've got a rule for division, and really all we need is the rule to determine the sign, because otherwise it's like working with whole numbers. So we've got that nailed down.